Filters. Everybody seeing the slide?
Yes, sir. Yep.
Okay. So we're going to talk about different types of filter networks, types of filters, applications, different characteristics, impedance matching, and digital signal process filtering. So basically, you got four types of filters. You can have a low pass, a high pass, a band pass, which is just a high pass and low pass put together, or a band stop, which again is a high pass and low pass separated differently. So for a low pass filter, it's defined as a filter that passes all the frequencies below its cutoff frequency. And its cutoff frequency is defined as where the attenuation is 3 dB down. So it's only going to pass half of the input power at that frequency and decreases from then on. So a typical first order filter would have a slope of 20 dB per decade or 6 dB per octave, although they always talk about decade. Octave means doubling the frequency. So your cutoff or corner frequency is going to be basically twice or half, depending on whether it's a high pass or low pass. And the impedance of the filter should be such that it matches whatever you're feeding it with. So if this is a filter, like a low pass filter on the output of your transmitter, it's probably going to be a 50 ohm characteristic impedance. So you design the circuit that way by the way you choose R and C values. Because you can not only choose them for a particular frequency, the ratio of them determines what that impedance is going to be. And you notice you also get a phase shift through that filter. So it's going to appear inductive until you get to the corner frequency or the cutoff frequency, and then it starts changing phase.
Bob, if the impedance is not matched, the filter characteristics go to hell in a hat basket.
That's true. And this is just showing difference in a pi and a t and what the relative values are. So when you kind of you calculate the frequency, and you come up with an L and a C. In the case of the T network, you divide the L's in half. So in other words, you split that inductor for that configuration. And likewise, if it's a pi network, you're going to split the capacitor value. And the cutoff frequency is similar to your resonant frequency formula, if you remember that one, Ed. 1 over 2 pi times the square root of LC. So the cutoff, in the case of a low pass, is going to be 1 over pi times the square root of LC. So the difference is there's no 1/2 in there. So it's twice the resonant frequency that you'd have for the fundamental. When we talk about the high pass, it's going to be 1 over 4 times the square root. And this other one is just showing, well, there's a formula for the characteristic impedance that you design it for. So you pick your Z value or R value and say 50 ohms, and then you figure out what LC ratio, the square root of it gives you 50 ohms. And there's also formulas for calculating the inductance and the capacitance versus the cutoff frequency.
Yeah.
In the high pass, very similar, except as I mentioned, the cutoff frequency is now 1 over 4 pi times the square root of LC. Because the cutoff frequency is below the fundamental. In other words, it's half of it. So what's the frequency above which a low pass filter's output power is less than half the input power?
Probably cutoff frequency.
Anybody familiar with Neppers? Really? I knew what it was once, but I don't anymore.
I heard of it.
What'd you say, Chuck?
I didn't say anything.
Oh. Okay, we talked about what? Was there a question?
There's one statement, yeah.
Yeah, the cutoff frequency.
Yes.
Okay, well, you're guessing pretty good.
Well.
Okay, a bandpass filter, like I said, essentially you've put a low pass and a high pass together to create one. So the low pass is going to give you the upper frequency cutoff, and the high pass is going to give you the lower cutoff. And some of the radios, like the ICOM, will let you do bandpass filtering, and you can actually get 2 bandpasses and move them together to either make it wider or make it narrower. And once again, you see that the phase changes. In this case, it's 0 at the center frequency of the bandpass, but it does go from plus 90 to minus 90 from one rejection region to the other. And we call the that outer band the ultimate rejection, which is its ability to attenuate or reject signals outside the pass band. So for a good bandpass filter, you might want it to be 70, 80 dB down at maybe twice the frequency out there. Insertion loss is how much attenuation is actually within the filter, how much you lose going through the filter. If it's an analog passive filter, you're going to have a few dB typically of insertion loss. So that half power point is taking the insertion loss into account.
I gotta go.
Okay.
I set up the camera for me.
Okay.
You got it on your phone? Okay. You doing your class? So I gotta move the cards around.
Okay.
Come on, Bentley, no.
So
All
the
right,
bandwidth of a
okay.
bandpass filter is
Okay.
measured between what 2 frequencies?
Alpha.
Upper and lower half power points or cutoff points. What term specifies a filter's attenuation inside the passband?
Insertion loss.
What term specifies the filter's ability to reject signals outside the passband?
Ultimate rejection.
Okay, a T network looks like the letter T. That's what I call a T network. It's normally in that configuration going to be a high pass filter. Because at low frequencies, these capacitors in series are basically blocking the signal. So it doesn't conduct until you get up to where this L and C combination is equal as far as reactance. And in this case, it's going to look capacitive at the lower frequencies and inductive at the higher frequency. So that's the same as what a series RLC circuit, right? If I can remember them right. When you operate it above its resonant frequency, it becomes
Baker.
High pass, B, Bravo.
inductive. So what's the frequency response of a T network with series capacitors and a shunt inductor?
High bypass. B.
The other configuration you normally see is a pi, because it looks like the Greek letter pi. It's typically what you're going to see as the matching network on the output of the power amplifier, where you tune the load and the plate. That's those two capacitors. Sometimes they'll add another inductor, and it'll be a pi L, which I think is probably the next chart. So the low pass is going to pass below the cutoff and block everything above the cutoff. It's pretty straightforward. It's just two capacitors and an inductor.
Is that a notch?
Is what?
Is it a notch filter?
No, that was just a low pass, which is what you normally use on the output of your transmitter because you want to reject the harmonics. So how are the capacitors and inductors of a low pass filter pi network arranged between the network's input and output? In other words, describe the circuit.
David. Delta.
Delta.
A lot of reading.
Yeah, they're very wordy. Yes.
Yeah, all. And general words in there.
Okay, you can use these as matching networks. So the intent is you want to match the output impedance of one to the input impedance of another, like your transmitter to your antenna. And what you're going to do is create the complex conjugate, which is why you use a Smith chart. So if you have, say, your antenna is a dipole and it's up high enough, it's 75 ohms, which is typical, but there's some reactance to it. It's not pure 50 ohms. So, or 75, but you want to match that to your 50 ohm transmitter. So you would figure out where, like if you were doing on a Smith chart, at what reactance will I cross the real axis at 1.5, because we're going to normalize to 50 ohms. So 75 ohms is going to be on 1.5 on the scale, or 50 would be 1. So you want to find that point and what the opposite reactance would be to cancel out and give you 0 reactance at 75 ohms. Well, excuse me, 50, because you got the 75 ohm point. It's a lot easier to do on the Smith chart when you know how to use it, but there's formulas that you can find online or in a book that do the same thing. But that's essentially what they're doing, is figuring out where that crossover on the real axis would be, which means you've canceled out the reactances, but you have an effective R. So you've actually changed the R value and eliminated the reactance. And also by playing with the Q of the components or the circuit, you can affect the bandwidth of it and how well it matches. The higher the Q, the narrower that match is going to be at a specific frequency almost. You have to have very low Q if you wanted to match an entire band. And some of the bands, there's no way you can do it. It's just too wide. So how does an impedance matching circuit transform a complex impedance to a resistive impedance?
Charlie,
A pi L network, we've got a pi network and we just add a series inductor. And what that does is give you more harmonic suppression, because it's going to, at higher frequencies, it's going to have more
A little bit.
impedance.
Okay. I'll keep the door open.
okay,
Bye.
bye-bye.
So you see that a lot of times in a vacuum tube final amplifier. Instead of just a pi, it might be a pi L. It doesn't affect the tuning. What describes a pi L network?
Additional series inductor.
Bravo. What's the purpose of adding an inductor to a pi network to create a pi L network? Okay, crystal lattice filters. You can make filters out of piezo crystals. And by having them at different frequencies, you can make a passband that has very steep skirts. I think the chart coming up shows kind of a one with just 4 crystals, but a lot of times they have more than 4. And they started doing that when crystals became cheaper, I guess. I don't know that you see crystal filters in radios much anymore, because it's better and easier to do in software with an SDR, and you can make a better filter.
Ceramics and ferrites are used also.
I didn't catch that.
Ceramics and ferrites are also used for mechanical filters.
Yes. The shape factor is one of the most important things, which is basically the steepness of the skirts and how flat it is on top. In other words, how closely it approaches just a square filter waveform, which you can't actually get. But the crystal filters are a big improvement over trying to do analog LC filters. You'd have to have 10, 11 stages to even get close. And that's a lot of toroids to wind. This is typical circuit, kind of what the output would look like. You'll see in this case, because it's only 4 and you're 2 different frequencies, you're seeing this ripple because you've got one frequency here and one frequency there. And where they cross over and add gives you this bump in the middle. So depending on how far apart they are determines how much of a bump. And if you added, say, two more, then you could have two more frequencies in there and get a flatter top. What is a crystal lattice filter?
Delta.
It's not Charlie.
Delta.
Yeah, this is a little because there was a subtle thing back here, which I don't know that I mentioned. Low level signals.
Oh, man. Missed that.
My bad.
You mean I can't use a, you mean I can't use a 10-pound piece of quartz for my power supply?
That's gotta be good.
Yeah. So which of the following describes a receiving filter's ability to reject signals occupying an adjacent channel?
Early shape factor.
That's your shape factor.
You want to reject adjacent signals. So what do you care about? You don't
Shape.
care about the top.
Oh, that's ripple.
You care about the edge, right?
Yeah, I'm sure.
You want it up and down, straight up and down if possible.
Yeah.
It's your shape factor.
Okay, we have different types of these analog filters. We've got Bessel's, Butterworths, Chebyshevs, and elliptics. For the exam, we only care about Chebyshev and elliptic. And they're very similar. The elliptic has steeper skirts, but it has less stop band ripple. The Chebyshev has more passband ripple. Excuse me. The elliptic has basically ripple in the stop band. In other words, you get it like it's shown here for that elliptic. It'll be way down, and then you get some bump ups. Actually, you can have peaks popping up much higher out here in the stop band. So its average attenuation in the stop band varies quite a bit. Whereas the Chebyshev is much better behaved in the stop band, but the trade-off is you got more ripple in the pass band. Whereas if you go something with a Butterworth or a Bessel, they're flat in the pass band, but they don't have nearly the slope on the skirts. So which type filter has ripple in the pass band and a sharp cutoff? I think they should have said more ripple in the pass band.
It's shovel shelf.
What are characteristics of an elliptical filter?
Echo. Charlie.
It's
Really? Although I don't know why they call them notches, actually. To me, you care about the peaks in the stop band. Digital filters. When you're doing these in software, basically you can implement any kind of filter that you can imagine. things that there's no way in the analog world that you could even come close to producing. So you can get essentially any kind of shape. You're kind of limited by processing power on how fast you can do the calculations in order to be able to work at a high enough frequency. So typically you will use like they're showing here, this transform in the middle, okay, which is the low pass filter, the shape that they're creating in software to filter the output of the analog to digital converter in the radio. So you've got, typically you still use an analog anti-aliasing filter, which is just a low pass filter so that you don't have any higher frequencies above the signal that you're looking for, because you wouldn't be sampling it enough, and you'd see that high frequency signal as a much lower signal. It's called anti-aliasing because you don't have more than 2 samples per cycle. Then you run it through this digital low pass filter and then back through a digital analog converter back to the analog world, where you may have another analog filter. That's just this very simple example of where you would have one. So which of the following is an advantage of a digital signal processing filter compared to an analog filter?
Alpha.
Yep.
Some different applications. One is a duplexer for a repeater, where typically you use a cavity filter. Has very low insertion loss and high selectivity, can handle a lot of power. There's a cross section of a typical one where you have a tuning knob that varies this slug, which I guess is changing the inductance. And then you've got these little coupling loops, and that thing acts like a big capacitor. So it's an LC network. I don't know any more about it than that. I've never actually twisted a knob on one.
Well,
I'm
it's
sure
fun.
Clyde has.
He said not to touch it. He said.
Not to touch it.
He said, don't touch it.
He probably got more than one too.
No, he screws.
Usually they'll gang them too. This is a different one, a helical filter, kind of similar operation. And you can make that into a bandpass or a notch filter. They're very high Q. Never actually had one in my hand, so I don't even know what the picture looks like. Which of the following filters is used in a 2-meter band repeater duplexer?
Oh, good old Bravo.
Which of the following is most frequently used as a bandpass or notch filter in a VHF or UHF transceiver?
Bravo.
Okay, so we talked about the different types of filters, cutoff frequencies, pi's and t's, and pi l's, matching, crystal filters, digital filters.